you another interference pattern, but it will be a shifted interference pattern. It will be complementary to that. So the position where you have a peak of the red interference pattern, you will have the crest here and the trough of the blue interference pattern. So this interference pattern will be shifted. If you add these two, total will give you no interference pattern. So particles detected in coincidence with either plus state or minus state, they should restore interference. So this is what is called the quantum eraser. So this concept was given by James in 80 and independently in 1982, in the modern form in 1982 by Scully and Joule. So let us summarize this path detection. So if you measure the P operator, that is essentially you are finding out which slit the particle is going through. State 1 tells you particle went through slit A, state 2 went through, particle went through slit B. On the other hand, if you, instead of measuring P, you measure the operator Q, which will give you the quantum erasure. So this will tell you that particle travel both slits A and B, because you can see that the state you will get is psi A plus B. So this indicates that particle went in a superposition of two paths. That is how you will get interference. Same thing for state minus. The particle traveled both paths, but only here the thing is that phase between the two paths is slightly different, the minus sign. So interference pattern is recovered. Okay, so let us come to this, what is now delayed choice interference experiment. So people wondered that can the choice of erasing, so here the thing is, you can see that we decide whether to measure operator P or operator Q. With operator P, you know which slit the particle went through, but you don't get any interference. But by measuring Q, you actually erase the which way information and you get back interference. So the choice is ours whether you want to erase the which way information or you want to get the which way information. So the question people ask is that, can this choice be delayed? Can one do that after the particle hits the screen? So particle has gone through the double slit and hits the screen, and you can look at the path detector later and you can still decide whether you want to measure operator P or whether you want to measure operator Q. So you can see that state of the particle and the path detector can be written as this. The same state can also be written as this. So as you can see from here, people who are familiar with entanglement, mathematical analysis doesn't put any restriction on when the path's information can be erased, because whether so whether you detect the particle first or these path detector states later, it should not make any difference in the results which you get. So if the path information is erased after the particle is detected, obviously it cannot affect the motion of the particle through the slit. But the implication seems to be that after the particle has hit the screen, if you measure operator P, you actually know that particle has gone through slit 1, slit A, and if you are getting the state 2, particle has gone through slit B. But if you had measured operator Q, then you know that particle has gone through both slits in both the cases. How can that be true? I mean, particle has already come and hit the screen. How can your choice, whether you are measuring P or you are measuring Q, can affect what the particle did in the past, whether it went through only one slit or whether it went through the other slit. So people were very intrigued by this possibility, and there was a lot of talk about whether this quantum eraser, it cause an effect backward in time, what is called retro-causality. So there has been a lot of debate on this delayed choice quantum eraser. Other thing you can ask is that, okay, theoretically it looks fine, but does it actually work in practice? If you choose this operator Q after the particle has hit the screen, will you actually get back interference or not? So let me just explain this, summarize, give you a concise summary of this delayed choice quantum eraser, what is happening. So setup is the following, that you have a source of particles and there is a double slit and there is a screen sitting here. And there is some kind of a which-way detector. Let us not bother about what is the nature of this which-way detector. So the particles emerge one at a time. They pass through this double slit, interact with in the process with this which-way detector, and then land at some random position on the screen. After the particle lands on the screen, one decides later, one chooses whether to read out the P observable or Q observable. If Q is read, particles in coincidence with the plus the eigenvalue, they show an interference pattern. So this does happen in the delayed mode also. And particles in coincidence with minus eigenvalue of Q, they also show an interference pattern, but which is shifted. Alternatively, if you decide to measure P, particles in coincidence with either of the two eigenvalues of P, they show almost identical continuous pattern, which does not represent any interference. However, if you don't do any coincidence with what your path detector is doing, if you just look at the screen, on the screen you will not see any interference. Interference is only in coincidence with this eigenvalues of this operator Q. So this is what happens in a real delayed choice quantum eraser experiment. So how people have understood is widespread belief, which is mostly due to Englert, Curry and Walther. There have been a lot of huge debate. Some of it.
Sorry, Tabish, can I interrupt you?
Yeah, sure.
There is one question on the this thing. Do you want to take it now or later, as you wish? It's probably relevant to what you are saying now.
I'll take it now. So, what should I do now?
Just on the side. Why I think I'll maybe try to read out the question. Why are psi AX and psi BX taken to be orthogonal? If the slit are not closely spaced, can psi A and psi B be non-orthogonal? That's the question.
So psi AX and psi BX, they have to be orthogonal because they emerge from two spatially separated slits. So since this state will be localized only at slit A and this state is localized only at slit B, so they are spatially separated, no overlap between these two, so they have to be orthogonal. Now when they travel to the screen, of course they will all spread out and they will completely overlap with each other. But since both of them undergo the same unitary evolution, they will continue to remain orthogonal. So psi A and psi B, even when they physically overlap with each other, they will still be orthogonal. If you take inner product of these two, it will still give you 0. So okay. I hope that answers the question.
Yeah. So on the, actually, if you look here below, there's something called a chat. If you click on the chat, you'll get to see these.
Since I have shared my screen,
I see.
I don't see the chat.
It's not showing. Okay, fine, perfect. Please go ahead. If there is some very pressing question, I will stop you.
Stop me and you can.
Yes, absolutely.
Yeah.
Yes.
So now there is a widespread belief, basically due to Englert, Curry and Walther. There was at one time, I think mid-90s, there was a huge debate in American Journal of Physics where this issue was discussed. And this widespread belief says that the choice falls to the experimenter, whether we want to know whether we registered an A slit atom or a B slit atom. Or are we interested in the complementary property of having plus minus states? So the view of this author, and which is as of now widely sort of followed, is that you can still choose after the particle lands on the screen whether you want to find out which slit the particle went through or whether you want to recover interference. But again, as I said, that this gives you a completely weird physical picture, no? That after the particle has landed on the screen, it did whatever it had to do while passing through the two slits. How can you choose later what the particle did when it was passing through the double slit? So now, can one understand this delayed choice quantum eraser better than what is given by this picture? So in the following, I'll try to simplify this quantum eraser setup so that it is easier to understand. In the meanwhile, let me just show you the various ways in which it has been physically realized with photons. I think this was the first one by Mendel in Nature. Then this last one, 2013, is by Zehnder's group. It has been done with atoms. It has been done with polarization of photons, and so on. So a lot of ways it has been experimentally realized, and people have actually seen that delayed choice quantum eraser actually works in practice also. So first, in order to understand what is happening and what is the physics behind this, let us try to understand what is the basis of inferring path information, because we say that state 1 tells us that particle passed through slit A, and slit B tells us particle passed through slit B, and so on. State 2 tells us particle passed through slit B. So let us understand what is the reason for inferring that. So reason basically comes from this entanglement. So consider just two spin-off particles, 1 and 2, which are entangled. So suppose the entangled state is like this: up for both particles plus down for both particles. So suppose these up and down states denote the eigenstates of the Z component of both the spins. So same state can also be written. I suppose by now you all know this quite well. Same state can also be written in this another basis, which are the eigenstates of the x component of the spin. So plus plus minus minus. So in this basis also, the state will look entangled. So measuring z component of spin 1 will immediately tell you the z component of spin 2. Because if you get up here, you immediately know that the other particle has up. If you get down for particle 1, you know the other particle is down. If you measure the x component of spin 1, it will immediately tell you about the x component of spin 2 that you can see from here. You get minus, and you know that the other particle is minus without measuring that. So this is the reason, so this is the basis for which we use for inferring the path information. But measuring this one should be very clear about this. Measuring the z component of the spin 1 cannot tell us anything about the x component of the spin 2 and vice versa. And measuring x component of spin 1 cannot tell us anything about the z component of spin 2. So there is a correlation between the z component of both the spins and x component of both the spins, but not between the z component of one and x component of the others.
Yes, sir.
Other. And these correlations, they work only as long as the entangled state exists, because the basis of this is because of this existence of this entangled state. If the entangled state is gone, then you cannot use that logic. So now suppose one measures the x component of spin 1, and so on spin 1, you have not measured spin 2. So now if I ask you, does a subsequent measurement of z component of the spin 2 tell us what the z component of the spin 1 was earlier? Because you know that information on z you can get from here. So you said that for second particle you are measuring the z component, but first you have measured the x component of spin 1. So does the subsequent measurement of z component of spin 2 tell us about the z component of spin 1 was earlier? That is, answer is complete no, because as soon as you did the first measurement, entangled state is gone. So once you get this x component of spin 1, either you get this answer or you get this answer. So that entangled state is gone. So later you cannot infer anything, you cannot do another measurement and make an inference on the other component. So now I will show you the equivalence between the delayed choice quantum eraser and entangled spin. So as you must have guessed yourself, so for spin 1, these up and down states could be equivalent to the two parts of the particle. So up spin of particle 1 is like particle going through the upper slit, and second down spin particle going through the lower slit. And these plus minus states of particle 1 are like particle going through both the slits in different ways. One with same phase in both paths and one with this 180-degree phase difference between the two paths. And for this other spin could be related to the path detector states. So these are the eigenstates of the P operator, these eigenstates of the Q operators, which we discussed earlier. So now, if the initial state is this is what we discussed earlier, a correlated state, the paths of the particle are correlated with the path detector states 1 and 2. So suppose if we are in the delayed mode, particle hits the screen first. So it will land at some position. So let us suppose it landed at a position x0. So of course, once it has already landed, then you have to do this. Take an inner product is x0. So you will get this number and you will get this number and then you will get this state. So now you see that this will tell you what will be the state of the path detector. This is not an entangled state, so entanglement is already gone. So after you have, after the particle has hit the screen, you cannot use entanglement to infer path information on that. So already you can see where is the fallacy of this earlier argument. They said that after the particle hits the screen, you can choose whether you want to measure P or Q. So already you can see that there is a problem with that logic. Now let us get this thing more concrete. Of course, from here we can see that there is a problem with the logic, but can we actually prove this, what is true? So let me give you a modification of this, not a two-slit experiment, but a quantum eraser using a Mach Zehnder interferometer. So let me just explain this setup. So there is a crystal and laser shines on that, and it gives out pairs of entangled photons. One travels in this direction and one travels in this direction, and traditionally these are called idler photon and signaler photon. So signal photon goes through this Mach Zehnder interferometer, and you all must be familiar with Mach Zehnder interferometer. I think yesterday or day before yesterday's talk was on this Mach Zehnder interferometer. And there are two detectors here. The idler photon, it goes here, and we put a polarization beam splitter here, and which will separate the polarization into two components, and there are two detectors here. So this crystal and this arrangement is such that these photons which are generated, they are entangled in the polarization. The state of the photon at the source will be this. So S subscript is for signal photon, which is coming here, and this I subscript is for the idler photon, which is coming here. So this is the entangled state. So this is the entangled state in the spin. So this is spin entangled state, and these are the special parts of the two photons. Special part is not entangled. So this is so I have also color coded. So wherever there is signal photon, I have labeled it this thing, put it in red color, and idler I have put it in blue color, so it will be easier for your eye to follow. So the modification from the standard Zehnder interferometer is that here instead of a conventional beam splitter, there is a polarization beam splitter. So what it does is that instead of putting this photon in a superposition of two parts, it will put in a superposition of two parts, but with different polarization. So one component will go here, the other orthogonal component will go here. Okay, so let me just tell you that if they were not entangled photon and this was just an ordinary beam splitter, what would happen? The photon will go here, it will take superposition of two paths. This path will go here, reflect from the mirror, and then it can go here or it can go here. Photon can take this path. Suppose this is not there to start with, it will reflect from this mirror. Either it goes here and either it goes here. So this is also a beam splitter. So then what happens in this setup is that all photons will land up at D1 and there will be no photon at D2. Because you can show that if the paths are correctly, phase differences are correctly tuned, there will be destructive interference here, destructive interference here. So this is like a double slit experiment. In double slit experiment, you get bright fringes and dark fringes. So this is a simplified form of this double slit experiment. Like all the bright fringes are merged into one single detector. So this is a simplified version of this double slit experiment. And all the dark fringes are sort of represented by just one detector, D2. So this is what happens in an ordinary thing. But here now we have a modified Mach-Zehnder interferometer. Okay. So let us see what happens. So this is the state to start with. After this signal photon passes through this polarization beam splitter, what happens? That it will split into two parts. The vertical part will go to this Part-2 and this horizontal polarization part will go to the upper path. So this horizontal part will go here and vertical polarization path will go here. So now the two paths also get correlated with this other photon. Now there is a polarization rotator. So now you know that in these two paths, polarization is now orthogonal to each other. But now here we have a polarization rotator. What it does is that in this path, it will rotate the polarization in such a way that it will become exactly equal to the polarization what is there in this path. So again, so the polarizations are orthogonal in these two paths, but here we have a polarization rotator which will rotate the polarization so that these polarizations become identical in the two paths. So what happens after the polarization rotator? So this HS will also become VS. So this path, second path was already VS. So this VS now goes out. So now you see that to start with we had two photons which were entangled in polarization. I have acted only on one of the photons and I have managed to disentangle the polarization of the two photons. So you see that polarization of the idler is here and this is the product state. So this is polarization of the signal photon. So you might wonder, and when I sent this paper for refereeing, one referee simply refused to believe that I am only acting on one of the photons. How can I cause this entanglement? So you know very well that if you have an entangled two entangled systems and acting on only locally on one of the systems, you can't change the entanglement. But here it seems to be happening. But this is actually not correct. Of course, polarization of the two have become disentangled, but now the paths of the signal photon have become entangled with the polarization of the idler photon. So the two paths of the signal photon have become entangled with the polarization of the other. So entanglement is not changed at all, only the entanglement has been transferred from the polarization to the parts of the other two particles. So this is something that is happening here. So two paths of the signal photon are entangled with the two polarization states of the idler photon. So why we have done this complicated thing? Because now it is very easy. So particle is going through two different paths, and polarization is same in both the paths. But now looking at the polarization of the other photon, which is far away, I can find out which path this photon is taking. So you can see that if I get V here for this idler photon, I know that the signal photon went through the path 1. If I get H, horizontal polarization, it went through the other path. So this is a clever way of getting which path information about this. So now before this particle signal photon reaches this second beam splitter, what is the state? The state is this. So as I already said that idler photon, this vertical polarization will tell you that signal photon followed path 1. Other possibility that it followed path 2. Now for this polarization of this idler photon, I can use another basis which is called right and left basis, which is a combination of this horizontal and vertical polarization. So these are two states. R is HI plus IVI and L is HI minus IVI. I can write this state in terms of these R and L states also. So the same state now looks like this. So here you can see that there is a possibility of quantum erasure. You might have seen that if you just look at this state, these is a superposition of two paths. So now this photon is far away from this. If you find R state of this, you know that the state of the signal photon was this, that means photon traveled both paths. If you get L, you know that the photon traveled both paths again, but with a slightly different phase between the two paths. Okay, so we have all the mechanism in place now. So what happens in the delayed mode? So let me tell you that this when I had formulated this, I thought this was a very new thing and nobody had thought of this, but later I realized that Zehningers have done not exactly the same, but a very similar thing. So in their experiment, this signal photon, so this is locally in their lab, idler photon is sent through some channel to another city which is 144 kilometers away. So you mean that, so what I mean to say is that this photon will land here first and this path information you will find much later. So this is 144 kilometers away. So this experiment has been done with Zehnder's score. So let us see what happens in the delayed mode. So in the delayed mode, of course, we have to worry about what happens when this photon lands at plus D1 and D2. So effect of the second beam splitter is also a unitary transformation. So it acts on psi1, it splits into two parts, D1 plus ID2, and this I2 part also splits into superposition of two parts. So now this state psi2 which I had taken, this one or this one, you take that and apply this beam splitter operator on that, and this is what you get. You might want to write this V and H in another basis. When you write this in terms of L and R states, you get this very simple state psi3. So this will be the state when the particles land here. in correlation with what is happening to this polarization of the idler photon. So now you see that this is a looks very simple, but it is very profound. Photon lands at D1, it tells you that the idler photon is in the L state. But L we already know corresponds to particle traveling both paths. This we've already discussed. L corresponds to photon traveling both paths, and R also corresponds to photon traveling both paths. So with D1 you get L state, with D2 you get R state. There is no other possibility. This entangled state straight away tells you that. So that means in the delayed mode, when the particle is landed on these detectors first, the state of the idler is already fixed. So this landing of that fixes that. So you no longer have a choice. And these both the possibilities, they correspond to erased path information. Particle has gone through both the states. So in the delayed mode, the path information is always erased. You can see it is very clear from this analysis. So now this was a simplified setup using Mach Zehnder interferometer. You might ask that does the same analysis work for a two-slit quantum laser, because there you don't have just two detectors, you have a screen and particle can land anywhere. So I can show you that this same conclusion, you will reach the same conclusion, but the analysis will be a bit more involved.
Tabish, can I just tell you, we have all total 10 minutes now.
Right, I know. Yeah, thanks.
So yeah, you can plan it as it suits you.
Right,
yeah.
right.
Okay.
I'll do that. So in a double slit quantum laser, what happens? So this setup I had already explained, that particle is going through the double slit, interacting with the path detector and landing randomly at some random points on the screen. And corresponding to one Q operator eigenvalue, you will get this blue curve. Corresponding to the other eigenvalue, you will get the red dashed curve. And both correspond to erased information.
I don't understand why.
Okay. But now you see that if I take photon has landed at this point, where this line hits this blue curve, what does it represent? It represents the probability of getting this plus state, right? The probability of getting this plus state, or rather probability that you have this psi A plus psi B. And this red dotted curve was in correlation with the minus state of the Q detector. So that means this represents the probability of getting minus state. But now you see look at these special positions where I have denoted this with this blue dots and red dots. So look at this blue dot, for example. So at this position, you can see that probability of getting, so this is probability of getting the minus of the Q operator eigenvalue. So probability of that is 0 at this point, and same at this point. So that the positions of these blue dots, the probability of getting minus is 0. So that means when the photon lands here, you are sure that the eigenvalue which you have got of the Q operator is plus and not minus, because probability of getting minus is 0. And this can actually be done in an experiment also. And once you know that once the particle lands at some special locations here, you know that the eigenvalue of P is plus 1. So that means it is in an eigenstate of Q is, eigenvalue of the Q state is plus 1. So you know that it has landed in an eigenstate of the Q operator, which corresponds to erase information. So when the particle lands at these special points, you already know that particle has gone through both the slits. Again, that argument doesn't work that you have the choice. You no longer have the choice. Just the very fact that the particle lands at these positions, it erases the which way information. You are sure that the particle has actually gone through both the slits. Now you will ask that what about the other points? These are only some special points you are talking about. So let me now show you this part. Even if you don't understand, let me give you an indication. You can look at the paper and understand it. So for quantum eraser, we had chosen this plus and minus states, which were these combinations of 1 and 2 and 1 minus 2. But I can choose a general mutually unbiased basis where I have e raised to power I theta. And these states which we had chosen earlier, they corresponded to theta equal to 0 here. So, but they are no secret states. If you choose this state as the state which you want to use for quantum erasing, still quantum erasing will be possible. But now the interference pattern which you will get will be not exactly centered at here, it will be slightly shifted. So this blue curve is what I am showing is if you have theta equal to 0, if theta is not 0, then this instead of blue curve you will get this red curve. If theta has another value, it will be slightly more shifted. So again you will get two complementary interference patterns corresponding to these two states, but now these positions will be slightly shifted. So this quantum erasing works perfectly even with this. So now the important point is that so now you see that you were asking now that why these special points? What about some point elsewhere? Now what I am saying is that any point here, it corresponds to the peak of some other pattern. So there will be some theta for which you will get an interference pattern for which this will be the peak. And that will tell you that particle has gone through both the slits. In other words, for every particle position on the screen x0, there exists a theta for which the probability of this thing is of getting the -1 is 0, and the path detector state is this one. And this you can also verify in the experiment also. So that means this shows that for particle landing anywhere on the screen, the path information is always erased, and you don't have a choice whether you want to look at the which way information or you want to erase the which way information. As shown in the delayed mode, when the particle lands first on the screen, the which way information is already gone. Okay. So let me just summarize now. Before the particle hits the screen, you still have a choice. You can choose either to read which path information or to erase it. And mind you, it is not just words. This part can be also experimentally tested. Whether you can put detectors in the path, whether this path detector states they are giving you correct information, particle is going through that particular path or not. All this can be experimentally verified. Erasing the which path information allows the possibility of recovering interference pattern. So this can be done before the particle hits the screen. If the particle hits the screen before the path detector is read out, what is called the delayed mode, then the path information is always erased. You don't have a choice. Okay, that's all I had to say. Thank you very much. I'll be happy to take questions.
Thank you very much for this. Thank you very much for this
wonderfully clear talk. I mean, it has a nice pedagogical element, and every slide was so clean and clear. Thank you very much. So now it's time for questions.